All right, folks, welcome to the acceleration notes. We're going to start at the beginning. This video is just going to go through the first and second page, so we will just do this first example, and we're going to take a look at how velocity time graph slope represents acceleration. So the different shapes of the line, positive or negative slope or no slope present, how that represents the acceleration that's happening. So for starters, we're going to take a look at the base equation for acceleration. You will definitely notice there's going to be more than one as time goes along, but we're going to be looking at this base equation here. A represents acceleration, delta V means a change in velocity, and delta T means a change in time. On the right hand side, they break this down a little bit more detailed. Anytime you see this delta symbol, which is the triangle here, it means a change, and in order to have a change you need to have two values. And the way that it's written here, it says V2 minus V1 or T2 minus T1. This is commonly written as VF minus VI, which means velocity initial and velocity final. Velocity final is the velocity at the end. So how fast is it going at the end of the scenario? Velocity initial is how fast it's going at the start. So we all know that V is velocity. That's been pretty standard all along. So there will be a change from start to finish. And then T2, T1 here on the bottom, again, is also written as time final, time initial. And again, that's the same thing. Final time is the time at the end, and the time initial is the time at the start. So the biggest process we're going to go through, just like any previous problems we've looked at, I don't care if it's velocity, like 3 variable equations and beyond, you always want to read the problem, you want to list the variables, and make sure you're using the appropriate equation. So really we have, I kind of look at it like there's 4 variables, even though there's maybe a little bit more than that. We have a change in velocity, which is made of 2 parts: velocity final, velocity initial. So I'm going to list those on the side. I know time final and time initial are 2 different things, but in most problems they're just going to give you a flat out just a time, and I'm going to just keep that as a single variable. We can call it delta T if we want. Sometimes they'll list 2 different start times, but oftentimes they'll just talk about an elapsed time. And in this problem, that's how it's laid out. And then obviously we need to figure out what is the acceleration. So if I list the variables first, I'll read the problem, and as I go through, I like to, maybe underline or highlight things that I know are variables, even if I haven't totally recognize which variable they go into. But as I read through, just kind of underline or highlight. If you got a highlighter or something, you can do this that way. Things that we need to know. Values are not always given numerically. Sometimes they're written out in word form. For example, of the very beginning of this, it says a pilot is at rest and starts to sprint across the tarmac, reaching a speed of 5.6 meters per second before he reaches his idling plane 8 seconds later. This at rest, the velocity at rest, this is the start, so there's velocity initial, and then the velocity final is here at the end. Just from that first sentence, I've already gotten 3, and then here we also have time. Just from reading that, I know that at the end, the velocity was 5.6 meters per second. At the beginning, they say rest is inferring that it's not moving at all. So that's a velocity of 0 meters per second, and the change in time here is 8 seconds. Now, I write a question mark by acceleration just to identify, hey, we do not know what acceleration is, but how do we figure that out? I'm going to write out the equation that tells us this. Acceleration is velocity final minus velocity initial, divided by, again, the change in time, which time final, time initial. This problem, they just give us a straight time of 8 seconds. So we're just going to put in the values for this. I know that the final velocity is 5.6, the initial velocity, initial velocity is 0, so they say they start at rest, so velocity final minus velocity initial, and then the time of 8 seconds. Really, now we just have 5.6 divided by 8, and that's going to give us 0.7. And the units for this are meters per second, which is a meter per second squared. This is the process I would like you to use for all of these base acceleration problems. Now, you will notice as we get further through the notes that there's going to be acceleration in different scenarios, or maybe where we're trying to find a distance given a velocity and or an acceleration. That's going to be separate. For now, this is all we're going to try to practice. These are the practice problems that we're going to work on, and this is what we're going to check for mastery, is just this application, just using this acceleration problem, equation, and we're going to solve various problems using this equation. There's different versions of it. We can rotate these around just like most three variable equations. I can solve for a change in velocity by knowing acceleration multiplied by a change in time, or I can figure out a change in time simply by doing a change in velocity and dividing by an acceleration. We'll see some more examples of that later. For now, we're just going to stick to solving acceleration given changes in velocity and time. Now, looking below here at the velocity time graph, I just want to make the relationship, because mathematically, when we're looking at what is acceleration, we know it's delta v over delta t. In the graphical world, I want to show how that represents slope when we have a velocity time graph. Remember, slope of a graph is always equal to change in y over change in x. So when you have a graph that has a variable on the y-axis that is equal to delta v, and one on the x-axis that is equal to delta t, then in essence, no matter what, for this situation, the slope is also going to equal the acceleration. Now, this is not the case on all graphs in general. You have to have these variables in these locations in order for that to be true. But one thing that's nice about this is when you look at a line, if it's going upward, so down here in the blue, we know that the slope is positive, which means the acceleration is positive. This person is going from 0 to 20 meters per second in a time of 20 seconds. We could figure out the rate of acceleration as we wanted to. Here in the red, it says steady speed. This just represents an acceleration of 0. It just means they're traveling at a constant velocity. They're not stopped, they're just not speeding up or slowing down. They are going 20 meters per second this whole time. This green line is a negative slope, which means they're slowing down. They didn't come to a stop, but they went from 20 down to 10 if you trace this across. And then this is a bit complicated, really, in an increasing acceleration. It's almost like a double standard, kind of like it's a plus plus, like your rate is going up, your acceleration, your velocity is going up, but the rate at which it's going up is going up. They call this jerk, is actually what it's called, but it's a little bit beyond where we are right now, but good to know for future reference. So with that, there's an example, and if you guys got questions, please let me know.